Okay, so we're going to start with an introduction to sequences here. So sequence, first of all, is usually denoted with braces, and usually it's denoted by a letter with a subscript, and this is an arbitrary n. It's a function whose domain is a subset of natural numbers, or sometimes the integers, really. But in any case, we say a sub 1, a sub 2, comma a sub 3, comma a sub 4, comma a sub 5, and so on. So it's just a list, basically. That's all sequences is, a list. And so A is the name of the sequence, and 1, 2, 3 is the name of the entry, basically. So for instance, if I have A sub n is equal to 1 over n, this is a fairly typical sequence, then we would have, if we start at 1, we'd have 1, 1/2, 1/3, 1/4, and so on. Okay? So here's an exercise. Find the 12th term of each of the following. Well, this is pretty easy. It's really just acts as a function in this case. So the 12th term of, if we call this one a sub n, the first one, a sub 12 should be 12 minus 3 is 9. The third entry of this, or sorry, the 12th entry of this, should be 3 times 12 plus 1 divided by 1 minus 3 times 12. Okay, 36, 37 over negative 35. Okay, and finally the last one, sine of 12 pi over 12. The 12's cancel, or sine of pi, which is 0. Okay, so the 12th of this is 37 over negative 35. The 12th term of this is 0. Okay, all right. So just a little bit of introduction. We'll play with these more in class. So the really important question here that we're going to be asking in a calculus context is what happened to a sequence as n approaches infinity. Okay, so we said that this sequence here is 1, 1/2, 1/3, 1/4, 1/5, and so on. We can see right away this is going to 0. Okay, we don't have to do much investigation. We can see this is decreasing towards 0. Okay, we can in some sense think of this as the limit as n goes to infinity. Okay, what's happening here? Well, n can only take on natural numbers, but in any case, it's still going to be going to 0. Okay, so sometimes we think of this as the limit as the index goes to infinity, but it's not a continuous function, so it's a little bit different. How about this one? Again, let's just take a look and see what it looks like. If we start with 1, we get negative 2 over 6. Put in a 2. We get negative 1 over 7. We put in a 3, we get 0. We put in a 4, we get 4 minus 3 is 1, 9, and so on. Okay, so this one's a little trickier to see. But what we can do is actually use our knowledge of limits to figure this one out. What happens as n is the index goes to infinity of this. Now we just have to remember that n can only be an integer value, so that's the only restriction on it, but this is still going to go to the same value as before. We can use L'Hopital's rule, or we can use the fact that this is n to the first power, n to the first power. And we can say this is the same as 1 over 1. This is going to go to 1. Okay. The continuous function n minus 3 over n plus 5 goes to 1, so its sequence does as well. Okay, so here's a little bit of terminology. We call this series convergent, or we say that the sequence, converges if it approaches a number as the index goes to infinity, where L is a real number. Okay, if it goes off to infinity, we say it diverges. Pretty straightforward. Very similar to what we saw in improper integrals. Okay, let's take a look at this. Notice the question here. Oftentimes the most important question is not what is the limit, but does it have a limit? That's often the more important part. So does n squared minus 1 over n converge or diverge? Well, what's going to happen here if we start choosing large values for n? We're going to have, say, let's start with 10. 100 minus 1 over 10. 11. 110. No. 11 squared. minus 1 over n. Notice the numerator is getting so much bigger than the denominator as we go up. If we start putting 1,000, okay, 0, 1, 0, 0, 0, 0, 0, 0, minus 1 over 1,000, okay, and so on. This is getting larger and larger. If we think of this as a limit again, then we can see that the numerator dominates the denominator, and this will go to infinity. This will be divergent. Now the one below it is kind of interesting because remember that we've been able to use up to this point our knowledge of limits to evaluate sequences, but 2 to the n is a continuous function. N factorial is not a continuous function. This one we have to do a little bit of work to figure out. Okay, remember that n factorial is n times n minus 1 times n minus 2 all the way down to 1. Okay, and we always define 0 factorial as 1. Okay, so if we start at 0 here, we get 2 to the 0 is 1. In fact, 0 factorial is also 1. If we put in a 2, we put in a 1 now, we get 2 over 2. That's also 1. So we have 1 and 1. If we put in a 2 now, so 2 squared. So this is n is equal to 2 over 4 over 2. Okay, it looks like it's getting bigger, right? Awesome. Let's keep on checking. Let's put in, this is 0, n equals 0, n equals 1, n equals 2. Let's put in n equals 3. We get 8 over 6. Okay. All right, so now we put in a 4. 16 over 24. Okay. Now we're going to need some calculator help. Okay, we have 2 to the 5th over 5 factorial. 2 to the 6th over 6 factorial. 2 to the 7th over 7 factorial. Let's take a look, use the calculator to see what's happening here. Now we can't use our theory of limits because the n factorial is not defined for non-integer values. Okay, so let's try this 2 to the 5th divided by 5 times 4 times 3 times 2 times 1. 100, oh, that's not right. 2 to the 5th. We need to use these. So we have 5 times 4 times 3 times 2. 0.266. Okay, for this one. Then we get 2 to the 6th. 6. Oh, we need parentheses. 6 times 5 times 4 times 3 times 2. 2 to the 7th. 7 times 6 times 5 times 4 times 3 times 2. Notice what's happening here. Initially the number started getting bigger. 1, 1, 2, and then it started getting smaller. And from here on out, this is tending towards 0. Okay, so this limit, or I should say, this sequence is going towards 0. Now we had no intuition about that before, but it appears what's happening is the n factorial is growing after a certain point faster than 2 to the n. Okay, which brings us to this notion of what happens when one sequence grows faster than another. Okay, so if we have two sequences, a sub n and b sub n, and we're looking at them as n goes to infinity, and we notice that both sequences are going to infinity. If a sub n over b sub n goes to infinity, and b sub n over a sub n goes to 0, what that means is that b sub n is tending towards 0 faster than a sub n. Okay, so a sub n is dominating b sub n as we go to infinity. So if we look back at this one, both 2 to the n and n factorial are going to infinity, and since this ratio is going to 0, n factorial is dominating 2 to the n. Alright, so we use this notation here to say one dominates the other. So we would say that n factorial dominates 2 to the n. All right, now here's a list of domination, which is kind of interesting. The biggest one we have is n to the n. Okay, that would be something like 1 to the first, 2 to the second, 3 to the third, 4 to the fourth, so on. That's always going to dominate n factorial, which will always dominate a number raised to n. Okay, that's what we saw here, which will always dominate n raised to a constant power. So that would be something like 1 squared, 2 squared, 3 squared, 4, and so on. That will always dominate the nth root of n, which will always dominate n to the negative k, where k is a constant. Okay. All right, so just that's something for us to keep in mind. We'll be looking at these later on as well. Okay, finally is one last thing we need to talk about, and that's this notion of monotonic and boundedness. Now, the idea of monotonic and boundedness is pretty straightforward. Monotonic simply means that after a certain point, we have a situation where every successive entry is greater than or less than the previous. So for instance, this sequence here, a sub n equals n, so this is going to be 1, 2, 3, 4, 5. This sequence is monotonically increasing, whereas when a sub n equals 1 over n, this is 1, a half, a third, a fourth. This is monotonically decreasing. This sequence sine of pi n, where we have sine of, we start with 1, or start with 0, sine of 0, sine of pi, sine of 2 pi. This is actually equal to 0 every time. So let's try another one. Let's try sine of pi over 2n. Now we have sine of 0, sine of pi over 2, sine of pi, sine of 3 pi over 2, and so on. This is going 0, 1, 0, negative 1, 0, 1, and so on. This is neither monotonically increasing or monotonically decreasing. Okay. However, this sequence here, the sequence that oscillates between 0, 1, 0, negative 1, 0, 1, 0, negative 1, has a property and it is bounded. Okay. So a bounded sequence simply means there's an upper limit or a lower limit. Okay. This sequence here is unbounded. It keeps on going towards infinity. This one is bounded below by 0. Okay. So the idea here, theorem 7.a is an interesting one, and it says every bounded monotonic sequence converges. Here's the picture. If we look at this sequence right here, we start at 1, go to a half, go to a quarter, we go halfway every time, basically. This sequence here is bounded below by 0 and is decreasing. If we have something that's always decreasing but has a lower bound, the limit always exists. Okay, the limit of the sequence always exists. Okay, likewise, if we have something that's always increasing but we know is bounded above by something, then this also has a convergent sequence. Okay, so that's what we're looking at here. If we're bounded on one side or the other and we're increasing or decreasing to that bound, then we are going to have a convergent sequence. Okay, that's it for today. Thanks a lot.